Hi everyone, welcome back. In this lecture, we're going to go over basic counting principles. Now in lecture 1, we used things like the binomial coefficient or the choice function. We used factorials, and that was basically just recalling some of the things that you probably saw in Macm 101. In this lecture, we'll actually go over those ideas with sort of a more rigorous foundation. So if any of those basic counting techniques we used in the first lecture were a little bit confusing or unfamiliar to you, we will be building them from the ground up in this lecture. So let's get started. I will note that most of the time my first lecture slide will consist of some question that I intend for you to just sort of read and ponder, pause the video, try to work it out for yourself right now. And this is just a prelude to what we're going to see during the course of this lecture. So here's a question about lattice paths, and a question about finding how many there are from a certain point to a certain point. You can pause the video, try it out for yourself. We will come back to, at the end of this lecture, we'll come back to this question and we will actually solve it in the lecture. So we're going to introduce two basic counting principles. These are the two foundational, fundamental, basic counting principles that we have that we're going to build everything off of. This is known as the rule of sum and the rule of product. So what the rule of sum is it says if there are m ways to perform a particular task, x, and then there are n ways to perform another task, y, then the number of ways there are to perform either the first task or the second task is m plus n ways. So the key observation here is to note that there is a sum there and the word or there. So if I want to perform one task or another task, the way I can do that, or how many ways I can do that, is the number of ways to perform the first task plus the number of ways to perform the second task. As opposed to the rule of product, which says, again, if there are m ways to perform task x and n ways to perform task y, then there are m times n ways, so there's a multiplication sign between those two. We simplify by just writing it as juxtaposition or next to each other. So it's m times n ways to perform both tasks x and y. Now I just want to draw your attention, this is the word and there. I think in the lecture notes booklet you downloaded, if you got to it earlier before I noticed the mistake, it might have had the word or there, but it should be the word and. So if your notes has the word or there, just cross it out and write the word and in. So the idea is the rule of sum is about doing one thing or another thing, and that corresponds to addition, whereas the rule of product is about doing one thing and following it up by doing another thing, and that's related to a product. Let's do an example to see how we can use these. So we'll imagine that we're at a restaurant and we've got a selection. So we're going to buy a drink. We've got a selection of 10 juices to choose from. There are 11 different sodas to choose from, and there are 9 different teas to choose from. So maybe our first question we can ask is, suppose I just want to order one drink. How many possible choices do I have for that one drink? So how many ways can I order one drink? Well, in this case, it's a question of getting a juice or a soda or a tea. And because this is an or, so I'm doing one task or another task or another task, then this is the rule of sum. So by the rule of sum, we have that there are 10 plus 11 plus 9 or 30 ways to order a drink. How about if we wanted to order one of each type. I want a juice, a soda, and a tea. So I'm going to order 3 drinks. So how many ways can I order one of each? So one of each drink. Well, in this case, I want a juice and I want a soda and I want a tea. So one nice way to think about this is imagine I've got, the slots on the tray that I'm going to carry these drinks out. And so I've got a slot that I'm going to put the juice in, I've got a slot that I'm going to put the soda in, and I've got the slot I'm going to put the tea in. There are 10 choices to fill that juice slot. There are 11 choices to fill the soda slot on the tray, and there are 9 choices for putting a drink in that tea slot. And so that means by the rule of product, we have 10 times 11 times 9, or 990 ways to order one of each drink. So that's just an illustration of the rule of sum and the rule of product. Those are our 2 fundamental counting principles. Let's go ahead and use them in another example. So suppose we have 10 people at a party. They all hug each other. How many hugs take place? How many hugs are there? So how are we going to do this? We've got those 2 fundamental counting principles, the rule of sum and the rule of product. Which one we use depends on how we want to solve this problem. In fact, we could use either one to solve this problem. So let's go ahead and we'll use the rule of sum. So how are we going to do this? Well, the way we would do it using the rule of sum is to break up the collection of all hugs into hugs that occur either here or here or here. So we want to insert that word or. So we want to be able to categorize a hug as taking place in this task or in this task or in this task and down the line. So the way we're going to do it is we're going to imagine that guests arrive at the party and they hug the current guests. So a hug will take place as a new person arrives. They hug all of the people that are currently at the party, and then they join the party members. And subsequently a new person will arrive. They'll hug all the party goers. And so that's how we're going to count them. So the situation is that we have a first guest arrives, and who do they hug? Well, the first guest will arrive. There's no one at the party. They're the first guest. So they hug, I guess that shouldn't be plural, they hug 0 people. And then the second guest arrives, and they hug, in this case it's not plural, Glenn, they hug the first party goer. So they hug 1, I was going to write people, but person, singular. And then how about the third guest? Well, when they arrive, they hug 2 people. And so on until the 10th party goer arrives. And when the 10th guest arrives, they hug, or hugs in this case, 9 people, the current 9 party goers. So there are 0 plus 1 plus 2 plus ... all the way up to 9. And so if we add up those numbers, that's equal to 45 hugs in total. And so we've done that by the rule of sum, because we're basically saying that any hug between two guests will take place as either the first guests arrive, or when the second guests arrive, or when the third guests arrive, and so on. We could do this another way. We could use the rule of product. And how could we do that? Well, in this case, we will imagine a hugging booth. So a place where the hugs take place. So we've got this hugging booth, and two people enter, they hug. It's an imaginary booth, but this is how we'll start to count these things. So one person will go on one side, another person on the other side, and they'll have their hug, and then we can count them that way. So when we think about it in this context, we can say, well, how many choices are there for a guest to occupy this spot in the hugging booth? Well, there are 10 choices. And then how many choices are there for a guest to be in here? Well, once one guest is in one side of the booth, there's only 9 guests left, so there's 9 choices for a guest here. And so we'll call this maybe, this is guest or person A and person B having their hug, and there's 10 choices for person A, there's 9 choices for person B. And so what that means is that there are 10 times 9, because we need to fill a person in slot A and a person in slot B, so there's an and there. There's 10 ways to fill A, 9 ways to fill B, so it's 90 ways to fill the spots in the booth. However, this counts each hug twice. So this counts each hug twice. Why is that? Because, for example, if Alice went in the A side and Bob went in the B side for their hug, then this would be counted as one hug, but the Bob going in the A side and Alice going in the B side would also get counted. But we don't want to count that twice, because Alice and Bob would have just hugged once. So we've actually counted every hug twice. Therefore, the total number of hugs is 10 times 9 divided by 2, which is 90 over 2, or 45. And so we can see we get the same answer as we had before. We just counted it in a different way. In this case, we used the rule of product, whereas in the first case, we used the rule of sum. So there's a nice example where sometimes when you first learn about the rule of sum and the rule of product, you think that the rule of sum only works in certain situations, namely the situations where you have ors happening, and the rule of product only happens in situations where you've got ands. And so the given problem will force you to pick one method over the other. But as this problem illustrates, depending on how you look at it, you can use either method to count. So now we're going to get into strings. We're just basically the combinatorial objects that we introduced in the first lecture. We're going to start to revisit them and start doing counting with them. And as we proceed through the course, we'll do a little bit more sophisticated counting with them. So we're just going to start with our basic counting of strings. In this case, if sigma is an alphabet with k letters, the number of strings of length n over that alphabet is k to the n. We actually used this in lecture 1, but here we're going to prove it, and we're going to prove it using our basic counting principles that we've just introduced. So the idea is we've got this string of k letters, so we'll go ahead and we'll write out our string. So here's where the characters would appear for our string. It's going to be n letters long, so n letters in length. This first character, because I'm choosing it from an alphabet of size k, there are k choices to fill that spot. But there are also k choices to fill the next slot. And there are k choices to fill the next slot, because I'm just looking at building a string. And a string is just a sequence of the letters in the alphabet. We can reuse the letters as many times as we want. And then there are k choices all the way down until the last spot. So what we have is, by the rule of product, how could I fill these spots with letters? I can fill the first one in k ways, and then I can fill the second one in k ways, and so on. So by the rule of product, there are k times k times k times all the way down to k, and there's n of those, or k to the n ways to fill the spots with letters. And so therefore the number of strings is k to the n. K to the n. And so that proves our theorem. And again, it just was following from the rule of product. So we've used this result before. Number of binary strings of length n was 2 to the n. There the alphabet had size 2. It was either a 0 or a 1 were our characters or our letters. So the number of strings was 2 to the n. We used that in lecture 1. In fact, we used it in lecture 0 with our warm-up counting exercise. Now here is the main result that tells us that assumption that was the number of binary strings of length n. So permutations now. How many permutations are there? Well, this says that the number of permutations of a set of n distinct objects is n factorial. So this is following that idea about strings, which we just did, because in building a string we can reuse the characters or the letters over and over. But in this one, to build a permutation, we can't use the characters over and over. Once we use a character, it's done. We can't use it again in the permutation. So the idea is we've still got our n positions, or our n spots, we'll call them. So our n spots, the places we can place these letters. And for the first spot, we've got n choices. For the second spot, I've already used one of the characters for my first spot, so now I only have n minus 1 choices left. And now I've used 2 of the characters, so I've got n minus 2 choices left for the next one. All the way down to, once I get to the final spot, there's only one character that's going to be left. So we got one choice here. So by the rule of product, how do we fill these slots? How many ways can we fill these slots? There are n times n minus 1 times n minus 2 dot 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 times 2 times 1, which is given in shorthand by this n with an exclamation mark, known as n factorial ways. Well, maybe I shouldn't even just say ways to fill the slots. There are n factorial permutations. The number of ways to fill those slots. And just to refresh our memory, that exclamation mark is read as factorial. Okay, so again, fundamental counting principle at play here is the rule of product. So now in the previous case, permutations were of n distinct objects. Now what if we want to look at permuting objects where some of the objects repeat? So this is known as permutations with repetition. So the idea is we've got k1 objects of a certain type, let's call it type A, another k2 objects of type B, and so on. And so when I've written this n equals k1 plus k2 all the way up to kr, it means we've got k1 objects of one type, k2 of another type, all the way down to kr of a final type, and the sum of the number of objects is equal to n. How many ways can we permute these objects? The number of ways we can permute these objects, this is a definition, so it's given by this symbol here, which is n choose k1, comma, k2, comma, all the way down to kr. That's how we'll read this. N choose k1, comma, k2, comma, k, all the way down to kr. So right now I've just introduced this notation that represents the number of permutations of these objects where there is repetition appearing. I haven't actually said how to compute this. We'll just have a look at this example and see how we could possibly compute this thing, and then the following theorem will tell us how we could compute this value. So here we've got the letters M, E, E, N, N. How many permutations are there? So here there's 5 objects. One is of type, the first type, which is just an M. There are 2 objects that are of the same type, E, and there's another 2 objects of the same type, N. So how many permutations are there? In order to figure this out, first we list the permutations starting with M. Okay, so normally, in the previous few lectures, we've talked about the ability to count without having to list. Here we're going to just start our investigations by listing some of these permutations. We're actually not going to list them all, but we'll list a few so that we get a feel for what's going on. So we'll start listing the ones that start with an M. So we've got an M. Now I've got 2 E's and 2 N's. Maybe I'll just list them as if they would appear in the dictionary if they were given as words. So we've got M, E, E, N, N. So in the dictionary, following this word would be ME, and then that final, or second E I should say, it could appear here, or it could appear here. And I'll fill in the N's for these remaining spots. And those are the only ones that are going to start ME. There's still more that start with M, it's just that these ones would start MN. And MN, and let's see how many we'd list here. So there's an MN, and if we were looking at them appearing in the dictionary, then we'd have a couple of E's followed by an N, or we'd have an E and an N and an E, or we'd have an M, N, N, E, E. And so there we go. So what we found is that there are 6 permutations that start with M. Now if we think about what we've done here, we've listed all the ones that start with M, but if I imagine just covering up the M temporarily, then what we have found is we have found 6 permutations of the pair of E's and the pair of N's. So I'm just ignoring the M for the time being. So there's 6 different ways to arrange 2 E's and 2 N's. And so this first M could appear in the start, or if I ignore it, I could put it here, right between. So E, M, E, N, N. Or if I ignore it, I could put it here. Or if I ignore the M at the start and instead put it there. So I've got a few different spots I can put the M in, inserting it between these 6. So what this means is M can be placed in 5 different spots. So it could be placed here, or here, or here, or here, or here. So at the start, or anywhere between the remaining 4 characters. So that means by the rule of product, since M can be placed in any of those 5 spots, once it's placed in a spot, The remaining spots can be filled in any of the 6 ways by the arrangements of the e's and the n's. So we have that there are 5 spots to put the m times 6 ways to arrange the e's and the n's accordingly, or 30 permutations. We've listed 6 of them, but from those 6 we've got the idea that there are actually 30. So that's one way we could do this. We started with the list and then we sort of extended from there. The other way we could do this is we could note that, the number of ways to permute 5 objects where there's 5 objects where there's 1 of type 1, 2 of a second type, and 2 of a third type is given by that value. That's the definition of above. If we know how to work out the value of this quantity, then we can determine the number of permutations by that method. The problem is, at this point in time, we don't know how to work out the value of this symbol, and that's where the next theorem comes into play. Now I'm going to preface our result in the next theorem by just seeing if we can figure out how to work out this value based on the work we've just done. So I've got 5 objects, I want to permute them. If they were all distinct, they were all different, so we didn't have repeated e's or repeated n's, then there'd be 5 factorial ways to write them out. The problem is, I'll add some subscripts here. So E1, E2, N1, N2. So if they were all different, so instead of being 2 e's, there was an e sub 1 and an e sub 2, which are different, then this word and this word, M, E2, E1, N1, N2, that would be a different word. That would be a different arrangement because the e's have switched spots. In this case, we are thinking of E1 as different from E2. The problem is they're not different. So when I do the 5 factorial for arranging distinct characters or distinct objects, if they aren't distinct, then I have to divide by the fact I've overcounted. So because the e's, if they get interchanged and they are the same object, you'll never notice that interchanging of them. So I would have double counted that same word, that M, E, E, and N. How many times would I have double counted M, E, E, and N? Well, I would have counted it twice because I could switch the e's and never notice, but I could also switch the n's and never notice. So I actually overcounted it by 2 times 2. In particular, what I get here is that if I want to think of them as distinct characters, so the e's are different and the n's are different, there's 5 factorial ways to arrange them, but they aren't distinct. I'd have to divide by the fact that there are 2 factorial ways to arrange the e's. 2 factorial is 2. There's 2 ways to arrange the e's, and I would have double counted those. There are 2 factorial ways to arrange the n's. I would have double counted those. There's 1 factorial way to arrange the m, or 1 way to arrange the m. I'm just adding that in there for sort of the pattern, just getting a feel for what the pattern is. So this is how we could compute this result. 5 factorial divided by 2 factorial over 2 factorial. Or in other words, what's 5 factorial? That's 120 divided by 2 times 2, or divided by 4, and there we get our value of 30. So there's a way we can compute the number of permutations without having to list them. In fact, without having to list any of them. That's what the next theorem says. The next theorem says that this symbol that represents permutations with repetition, if I had n objects, k1 of one type, k2 of another type, all the way down to kr of a last type, then that is equal to n factorial over k1 factorial times k2 factorial times and so on. Oh, I notice here that I have commas, but these really should be multiplication signs in between. These quantities multiplied to each other. And the proof of this is precisely what we said on the last page. If all n objects are distinct, so they're all different, there are n factorial permutations. So here we're going to suppose there are k1 A's, and we'll list them as A1, A2, dot, 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 up to AK1. So they are, in the context of permutations with repetition, these are the same A's, but if I want to imagine they're distinct, I will add subscripts to them. And so now I'm imagining they're all different, so then when I count the permutations of all these objects, there's n factorial permutations. So those K1A's, I'm imagining I've just added subscripts to them. And so what would an arrangement look like? An arrangement has the form, it looked like there's a bunch of characters of all the different types. Maybe I'll add some dot, dot, dot. So we'd have an A1 appearing somewhere. Maybe there was an A2, and then the A3 appeared somewhere, and then the AK, all the way down to AK sub 1 appeared somewhere. Maybe there's more characters on the end. So we've got the A's distributed. So that would be a permutation where they were all distinct. But this permutation would get counted different from arranging the A's in those positions. So switching the A1 and the A3, for example. That would give us a different permutation if I'm thinking of the A's as distinct. But it would give us the same arrangement if I'm imagining the A's all to be the same. So how much have I overcounted by? So this would be counted K1 factorial times, since there are K1 factorial ways to arrange the A1, A2, all the way up to AK1. So the idea is if I imagine they were all different, then the words I create with the A's in these positions where their subscripts were all switched around, that would account for K1 factorial different arrangements, which would all be considered the same as soon as I forgot subscripts. So what that means is that, therefore, n factorial overcounted the number of permutations by K1 factorial, and then also the arrangements of the objects of the second type, K2 factorial, all the way up to the number of objects of the other type being arranged, Kr factorial. So there are n factorial over K1 factorial, K2 factorial, up to Kr factorial permutations with repetition. And that's what we wanted to prove. So we used the fact that the number of permutation of distinct objects are n factorial, and then we adjusted for the fact that some of these objects are the same type, and so we overcounted and divided by how many times we overcounted. And if we think about where the factorial came from, it came from the rule of product. And so all of this boils back down to our two basic counting principles, rule of sum and rule of product. So let's look at an example. How many binary strings of length 20 are there with exactly 13 ones? So we want binary strings of length 20. So there's going to be 13 ones, and there will be 7 zeros. So we want to make a binary string out of 13 ones and 7 zeros. You can think of this as the number of ways to permute the 13 ones and 7 zeros. And so that's permutation with repetition. So we are permuting 20 objects, 13 of them are one type, 7 of them are the other type, so that is 20 factorial divided by 13 factorial over 7 factorial. And that's the number of binary strings there are with exactly 13 ones. So I want to just pause here and just mention that we have introduced now what is quite a powerful symbol. This symbol here, where the top number, in this case it's 20, but in general, the top number n, and the bottom numbers sum up to n, and that is the number of ways to permute that top number, that 20 objects, where 13 of them are of the same type and the other 7 are of the same type. It's a very powerful notation to represent the number of objects that the number of objects that we're trying to count. And our previous theorem tells us exactly how we can evaluate this very powerful symbol. It's 20 factorial over 13 factorial, 7 factorial. So now what we're going to do is we're going to introduce the binomial coefficient that you probably are familiar with from Macm 101, but we're introducing it as a special example of the one we just talked about. So if S is a set of size n, the number of subsets of size k is given by this symbol, n choose k. That's how we read this, n choose k. So we read this as n choose k. And it is equal to n factorial over k factorial times n minus k factorial. Or in other words, it is equal to, in terms of our previous symbol, n k comma n minus k. So it's the number of ways to permute n objects where there are k of one type and n minus k of the other type. So why is that? Why is this particular symbol, n choose k comma n minus k, why does that equal the number of ways there are to select k objects from n objects? That's what we're going to want to prove here. And so how do we do that? Well, let's let the set S be S1, S2, all the way up to Sn. So this is our set of size n, and we want to figure out how many ways there are to make subsets of size k from this set. So each subset of size k corresponds to a binary string of length n with k ones. Why is that? Well, let's just think about a particular example. So I'll do a particular concrete example. Let's say our set S is S1, S2, S3, S4, S5. So n is 5 in this case, and k is equal to 3. Just for concreteness, so we can see that the statement I just wrote down, each subset of size k corresponds to a binary string of length n with k ones. We can see that this makes sense through this one example. So that means a binary string of length 5 with 3 ones. So for example, 0, 0, 1, 1, 1. So there's a binary string of length 5 with 3 ones. That should correspond to a subset. And so what I'm going to do is I'm just going to say the zeros and the ones are just answering the question, is this element in the set? A 0 says no, a 1 says yes. So is S1 in the set? This is telling me nope. Is S2 in the set? Nope. Is S3 in the set? Yep. Is S4 in the set? Yep. Is S5 in the set? Yep. So I'm just reading 0 as no and a 1 as yes. So this corresponds to the set S3, S4, S5. Similarly, if I had a subset, let's say S1, S3, S5, so a 3-element subset, that would correspond to a binary string of length 5 with exactly 3 ones. There'd be a 1 in spot 1, a 0 in spot 2, a 1 in spot 3, a 0 in spot 4, and a 1 in spot 5. So there's our correspondence. Each subset of Sk corresponds to a binary string of length n with k ones. Now I've illustrated that through an example. Examples are never enough in a general proof, so I actually really want to specify how we could do this in general. So here's how we do this in general. We say, I've said each subset of size k corresponds to a binary string of length n with k ones, and so what that means is we construct the binary string as follows. So the binary string b1, b2, all the way up to bn is constructed in the following way, where bi is equal to 1 if si is in the subset, and bi is equal to 0 if si is not in the subset. And so that's how we can associate to a subset a binary string. And now the question is, how many subsets are there? So the number of subsets of size k, well, that's now equal to the number of binary strings of length. In this case, it's length n with k ones. And how many binary strings are there of length n with k ones? There's n, choose k, comma, and minus k, because that's k ones and n minus k zeros. And so that was basically our previous example. Our previous example was about how many binary strings are there of a particular length with exactly this number of ones. In this case it was 20, choose 13, comma 7. In general it would be n, choose k, comma, n minus k. And that is precisely n factorial over k factorial n minus k factorial. And that's what we are calling, in this theorem, we've introduced the notation n choose k as a shorthand for that. And so there we go. If you think about what we've done now, we have introduced the binomial coefficient, which you probably saw in Macm 201 or Macm 101, this n choose k. But we've introduced it now through permutations with repetition, and all of that followed from, or was built up from, the rule of product. So we've now developed this choosing function and the formula that generates it, n factorial over k factorial times n minus k factorial. All right, let's look at a final example. Lattice paths. So what we want to do is we want to determine how many lattice paths are there from 0, 0 to 6, 4. So the way we're measuring this here is, 0, 0 is here, so it's 0, and then there's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, and so 6, 4 is this point up here. And I want to know how many lattice paths are there connecting the lower left dot to the upper right dot. And by lattice path I just mean, if we think of this as a network of roads, how many different ways are there to travel by only going east and north? How many ways can I get from the lower dot to the upper dot? So maybe I'll just show a couple of different ways here. I can overlap a little bit with them. So there's 2 different paths going from the lower left, or the start, to the end. how many paths are there in total? The way we want to answer these questions is we want to connect them to the counting objects that we've been introduced in lecture 1, but we've also learned how to count in this lecture. So for example, we've now learned how to count the number of subsets of a particular size from a given set, or the number of permutations of an object, or the number of binary strings with a set number of ones in it. So these are various objects we've learned how to count now, and we're going to see if we can attach to this one of those counting objects. So how can we do that? Well, let's just imagine these lattice paths and try to encode the information. So 2 paths shown can be encoded or written as, well, let's see, what is the first one? The first one, which was our orange one, it went north, east, east, north, north, east, 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 north, east. So there is an encoding of our first path. It's just a set of instructions as to how we can travel from the start to the finish. How about the next one? Well, it went east, north, and then 2 east moves, and then 2 north moves, and then 3 east moves, and then a north move. And so the thing to notice is these are permutations of 1, 2, 3, 4 north moves, so 4 ends, and 6 e's, because we went from 0, 0 to the eastern point 6 and the northern point 4. So in order to get there, I would have had to move 6 times in the eastern direction, 4 times in the northern direction. So now we've reduced this to a problem of how many paths are there. It's just really a question of how many permutations are of these 10 objects, where 4 are one type and 6 are the other. So the number of paths is equal to the number of permutations of 4 ends and 6 e's. And that's given by 10, choose 6, 4, or 10 factorial over 6 factorial, 4 factorial. So that's one way to do it, is to just connect it with these words in two of these letters, N's and E's, where one letter appears 6 times, the other letter appears 4 times. Maybe we could think about an alternate solution. So alternate. So the number of paths is, well, what I have to do is I have to give it 10 instructions. They involve north or east. 6 of the instructions have to be eastern moves. 4 of them have to be northern moves. So I've got this list of 10 instructions. Maybe I'll write them down here. 10 instructions. And these 10 instructions could be, from these 10 slots, I'm going to pick 4 of them, which will be my northern moves. So I'll pick 4 slots, that'll be the northern move, and then the remaining ones will be the eastern moves. So that would be, of those 10 slots, pick 4 of them to be the eastern moves. So that's like the number of ways to pick from a set of size 10, which is our 10 slots, and a subset of size 4. And so there's another way to write down. The number of paths is 10 choose 4, which is 10 factorial over 6 factorial, 4 factorial. So either way you look at it, we get the same result. One way was about picking subsets of a certain size from another set. Another way was looking at permutations with repetition. And as this section shows you, that the counting involved in these objects is all really the same type of counting. All right, that's it for this section. Thanks for watching, and we'll see you again next time.